Hello everyone, welcome the video lecture series on circuit analysis. In the last session we have seen series circuit and voltage divider circuit or principles of voltage divider. That means how the elements are connected in series and how can we determine the equivalent resistance for series connected resistors and how the voltage will be divided among the series connected resistors with using the principles of voltage division. Okay. Today we'll see the parallel circuit and current divider rule. You can consider voltage divider rule, series circuit, and parallel circuit connect with the current divider rule. Okay. So when we are saying two elements or branches or devices are connected in parallel, if they have 2 points in common as shown in the circuit given below, you can consider here, for example, you can consider all the elements are connected in parallel. That means they share 2 points in common. That means one pair of, for example, you can consider R1 and R2. Okay, one pair of their terminals is connected at this point, and the other pair of the R1 and R2 are connected at this point. So they share 2 points in common. So if this condition is fulfilled, so we can say that the circuits are connected in parallel. So as you can see, the voltage source R1, R2, R3 up to Rn, they share 2 points in common. 2 points in common. The other, that means one terminal of V1, R1, R2, R3, as well as Rn will be connected at this point, and the other terminal of V1, I mean the source voltage, R1, R2, R3, and Rn will connected at this point. So as you can see, the elements are connected in parallel. So for this circuit, it has 2 nodes. As you can see, more than 3 elements are connected at the 2 nodes, node A and node B. So basically, this is the principal node. Okay. For the parallel circuit, the voltage is constant. Okay, the voltage across each element, across each parallel connected resistor will be constant. That means V, which is equals to V1, which is equals to V2, which is equals to V3, which is equals to VA. That means for parallel connected resistors, the voltage across or the voltage drop across the resistors will be the same. This is very important. Just like that of series connected resistors, the current pass through each series connected element will be the same. Okay. And the other one is let's apply KCL. Apply KCL, Kirchhoff's current law at point A, or node A. Okay, at node A. That means we have the total current I and we have the currents divided among the parallel connected resistors. You can remember from series connected resistors, the voltage will be divided among the series connected resistors, like that of series connected resistors. The current or the total current will be divided among the parallel connected resistors. So we can write I, the total current, which is equals to I1 plus I2 plus I3 plus IA. That means I1 is the current pass through resistor R1, I2 is the current pass through resistor R2, the I3 is the current pass through resistor R3, and IN it is the current passing through resistor RA. So using Ohm's law or Ohm's law, okay, we can write I1 which is equals to V over R1, I2 which is equals to V over R2, I3 is equals to V over R3, and then IN which is equals to V over RA. Okay, we can substitute this expression into this expression. Okay, and we know also I, which is equals to v over, we can substitute this expression, so we can have I is equals to, okay, v over r1 plus v over r2 plus v over r3 plus v over r. Okay, I can write v into 1 over r1 plus 1 over r2 plus 1 over r3 plus 1 over ra. Okay, I can write this one. So I over v which is equals to 1 over r1 plus 1 over r2 plus 1 over r3 plus 1 over ra. Okay, but we know that I over v, which is equals to 1 over r equivalent. That means we know that v over I, which is r equivalent, so 1 over r equivalent, which is equals to I over v. So I can write 1 over r equivalent, which is equals to 1 over r1 plus 1 over r2 plus 1 over r3 plus 1 over ra. Okay, ra. So from this I can write 1 over r equivalent, which is equals to summation of 1 over ri. I runs from 1 up to n, where n is the number of resistors connected in parallel. Okay, so we can say that the inverse of the total resistance value of parallel connected resistor will be the summation of the inverse of each resistors connected in parallel. Okay, in parallel. So the equivalent resistance are equal to n resistors connected in parallel is given by this expression, which is summation of 1 over ri. I runs from 1 up to n. So R equivalent is always smaller. This is very important. R equivalent is always smaller than the resistance of the smallest resistor. In parallel combination. Okay, that means you may have any number of resistors connected in parallel, and from those parallel connected resistors, we'll have the minimum value in the parallel connected resistors. So R equivalent should be less than the minimum value of the resistors connected in parallel. Okay. And the other very important point is, if any number of resistors with equal resistance value are connected in parallel, then their equivalent resistance will be R over N. For example, you can consider these resistors. Okay, these resistors. So this is R, this is R. So if we are asked to determine R equivalent for R, the two resistors connected in parallel, okay, so we can write 1 over R equivalent, which is equals to 1 over R plus 1 over R. So I can write which is 2 over R. So from this R equivalent, which is equals to R over 2. So as you can see here, the number of resistors connected in parallel are 2, and their values are the same. So their equivalent resistance will be one resistance value divided by the other by 2. Okay. If 400 ohm resistors are connected in parallel, so definitely their equivalent resistance R equivalent will be 100 over 4, which is equals to 25 ohm. Okay, as you can see here, the equivalent resistance is less than the 100 ohm resistor. Because 100 is the minimum value of the parallel connected resistors. So that's how we can determine the equivalent resistance. So one thing you need to notice here for parallel connected elements or resistors, the first one is the voltage is constant. The current will be divided among the parallel connected resistors. If the equivalent resistance will be, or the inverse of the equivalent resistance will be the sum of the inverse of each resistors connected in parallel. And if any number of resistors with equal resistance values are connected in parallel, so the equivalent resistance will be take the one value and divided by the number of resistors. Okay, that's the very important point to be noticed here in parallel connected circuits. Okay. We know that basically R1 over R equivalent, which is equals to 1 over R1 plus 1 over 2 plus 1 over R3 plus 1 over RA. Okay, 1 over R1 it is the conductance, 1 over R2 which is G2, 1 over R3 which is G3, and 1 over Rn which is Gn, and 1 over R equivalent which is the total conductors. So if any number of resistors are connected in parallel, so their conductance will be the sum of each conductance or each conductance of each resistor. Okay. As the number of resistors connected in parallel increase, the input current level will also increase, because the total current, the total resistance will be reduced. So the current will be increased. Because I is equals to V over R equivalent. If you increase the number of parallel connected resistors, R equivalent will be reduced, so the current will be increased. Okay, the current will be increased. So voltage is always the same across parallel elements. This is very important. And R equivalent is always what I have said before. It is smaller than the resistance of the smallest resistance value of connected in parallel. Okay. For single source parallel network, the current IS is equal to the sum of the individual branch current. So that means if you consider this one plus minus, this is Vs. Okay. So you'll have this one. So this is IS. So this is I1, and this one is I2. So IS, the total current will be I1 plus I2. For parallel circuits, the greatest current will exist in the branch with the lowest resistance. If you remember from series connected resistors, you know that the resistance which has the highest value of resistance value will share the highest value of voltage from the source. Okay, from the source. Here in parallel connected resistors, the resistor with the smallest resistance value will share the highest current from the source current. That is very important. The analogy of series connected resistor. Okay, the analogy of series connected resistor. The resistor with the highest resistance value will share the highest voltage from the source voltage for series connected resistor, whereas in parallel connected resistors, the resistors with minimum resistance value will share the highest current from the source current. Okay, so that's very important. Okay. So from this I can write this is the total, the source voltage. So Is, which is E into 1 over R1 plus 1 over R2. Okay, 1 over R2. So you can take the LCM R1, R2, which is R1 plus R2. Okay. So Is, which is equals to E into R1 plus R2 over R1 plus R1 times R1 times R. So we can we can use this how we can determine the source current, Okay. So power distribution is the same. That means we will have the power delivered by the source, and we have the power absorbed by or dissipated by the resistor. So the total power which is supplied by the source, which is equal to the sum of the power absorbed by each resistor. The power absorbed by each resistor. So the power relationship for parallel resistor circuit is identical to that of a series resistive circuit. Okay. When it comes to current divider rule, shows that the total current shared by two resistors connected in parallel is inverse proportion to their resistance value. If you remember from the series connected resistors, the voltage will be in direct proportion to the resistance value of the resistor connected in series. Okay. For two parallel resistors of equal resistance value, the total current will be divided equally. That means if you consider, okay, this is R and this one is R. So this is source voltage, okay, and this one is source current. So the current which is passes through either of the two resistors with equal value will be IR is equals to IS over, okay. The current will be divided among the I mean divided, half of the current will be divided or flowing through the resistor. For two parallel resistors with different resistance values, the smaller resistance, the greater the share of the input current, which is what I have said before. Okay. So that's how we can consider parallel circuit and the current divider. Okay. I mean the properties of parallel circuit. Okay. Now let's consider current divider circuit. Okay. So as you can see here, I is equals to I1 plus I2. This is a total. That means if you apply KCL at this point, it is entering the node, and I1 and I2 they are leaving the node. So the current entering the node, which is equals to the sum of the current entering the node, which is equal to the sum of the current leaving the node. Okay. So I1 can apply V over R1 and I2, which is equals to V over R2. Okay. And I, which is equals to V over R equivalent. Okay. R equivalent. So was R equivalent for the parallel resistors? R equivalent, which is equals to R1 times R2 over R1 plus R2. That means you can consider 1 over R equivalent, which is equals to 1 over R1 plus 1 over R2, which is R1 plus R2 over R1 R2. So if you inverse it, R equivalent, which is equals to R1 R2 over R1 plus R2. Okay. So this is the equivalent resistance for two resistors connected in parallel. Okay. So I can write the value. Okay. And using this, we can have the voltage. That means we know that I is equals to V over R equivalent. So V is equals to I times R equivalent. So which is I times R1 R2 over R1 plus. Okay. Now let's have I1, which is V over R1. As V, it is expressed here, which is equals to 1 over R1 times V times R1 R2 over R1 plus R2. So R1 will be cancelled, which is equals to V times I mean, this is the current, total current. Okay. So which is I times R2 R1 plus R2. Similarly, I2, which is equals to V over R2, which is equals to 1 over R2 times I times R1 R2 over R1 plus R2, which is equals to A. So R2 will be cancelled, so you'll have I times R2 over R1 plus R2. So this is how we can determine the current among the parallel connected resistors. Okay. So that's all for this session. Please share, like, and subscribe to the channel so that it will be accessible for others. Thank you very much.